So I just want to come back to this solution for the velocity and say a few things about it. This is the function that we derived by separating variables. This is the graph. Just remember that, let's go back to this idea that we said that the mass times gravity should be equal to that constant times the terminal velocity. That was the substitution that we made early in the problem. And so it's worth noting that the terminal velocity is going to have a dependence on the value of the mass and the value of this constant k. So in other words, imagine if you fill your beach ball with sand. If you fill the beach ball with sand, you're changing the mass. All right. So when you increase that mass, what's going to happen is the beach ball is going to basically not be affected by air resistance as much, and it's going to fall and accelerate a lot longer before it reaches terminal velocity. And the result is that it's going to reach a much higher terminal velocity than an empty beach ball. Okay. The other thing is that K factor, and K is kind of how strong the drag force is. If K is very strong, like you're dropping a beach ball through like a really thick gas or something like that, well, then the terminal velocity that it reaches should be smaller. So by making K larger, that should have the opposite effect, and the object should not reach quite so high of a velocity. So coming back to this formula that we have up here, you can actually rewrite this a little bit by doing that substitution. You can say that the velocity as a function of time is equal to the terminal velocity times 1 minus e to the negative. And what I'm going to then do is a substitution here by saying that I'm going to substitute for k over m. So I'm not going to write k over m, but if you look at this, right, we have m over k right there. So m over k should be equal to Vt divided by g. So that means I can substitute here and I can write my constant in different terms. Okay, so instead of writing it as k over m, I can write this in terms of g, the acceleration of gravity, divided by the terminal velocity of the object. Okay. This is going to be kind of hard for me to show in this graph, but if you go back to this case, well, what does that mean? If you have a beach ball that's filled with sand, a couple things are going to happen. One of them is that the terminal velocity is going to become much larger. Okay. The other thing is it's going to take a lot more time for the beach ball to reach that terminal velocity. So I guess it would be something like this. This would be for a big mass. Okay. You would basically have a new terminal velocity, which is much larger, and it would take the mass longer to reach that terminal velocity than it took in the original. So this is my original here. If you look at the other case, what if you have use a drag force which has a lot more resistance? Well, the effect there is going to be to reduce the terminal velocity, and it's also going to allow the object to reach that terminal velocity faster. So what's going to happen in that case is something like this. You'll reach a smaller terminal velocity, and you'll reach it a lot faster. This is like dropping an empty beach ball through a very thick gas of some kind, I guess. Okay. So that's something to think about, and especially as you start doing problems, is to think these are two different ways of representing the velocity. So, okay. So let's just do the last part of the calculus here. Let's derive the acceleration as a function of time. This should be a pretty straightforward thing to do. Don't worry, we don't have to separate variables on it. But what we're going to do is just say that acceleration is a function of time, should be equal to the derivative of velocity with respect to time. So we're going to take the derivative of our previous solution here. Okay, so that's going to be equal to d dt, and then I'm going to write it that way. Okay, so this is actually our solution from before. I multiplied the terminal velocity term out to make it easier, but it's really the same thing as what we have up here. Okay, and the reason I multiplied that out is because I hope you can see that this term here just goes away. The derivative of a constant should be nothing, and then you're left with the derivative of this. So let's do the math on that. So that goes away, and you're left with negative Vt. When you take the derivative of an exponential, the exponent comes in like so. Otherwise, the exponential is not affected. Okay, and then you just kind of simplify your terms. These negatives are going to cancel out. And again, for my terminal velocity, I am going to substitute in mg over k. Again, coming back up here to this relationship. Because I can see then that some stuff cancels out. Ooh, that's nice. A lot of stuff cancels out. And my final answer is that the acceleration as a function of time is equal to g times a negative exponential. Okay, and that's a really nice result because that is an easy one to graph, and it totally matches our prediction, which says that we expected the object to accelerate initially at g, and then to drop off and accelerate less and less as time goes on, eventually approaching 0. So this is basically just the graph of that function. And now you know that this is actually an exponential curve. And so the acceleration should decrease exponentially as time goes on. Okay, so that is what we have. Again, if you really wanted to, you could rewrite this. By replacing k over m with g over terminal velocity. And that also works for the same reasons as we said before. So either way you want to use it, that is your final formula.